So hopefully you'll recall from last time we started talking about the foundations of logic, and the first thing we said is that logic is built up out of statements, and then also connectives which connect and operate on those statements. Now, just to flip back for a second, what is a statement? A statement is something that is either true or false. Exactly. Now there are fancier forms of logic where that's not always the case. There's actually a lot of current research going to that right now. But for our purposes, in logic that's been studied for well over hundreds of years, true and false is our end result. So, for that reason, we need to understand true and false in all of the possible combinations. So what we're going to do right now is the way to write out to discuss all the different cases of things being true and false. The way we set this up is called the truth table. So the very first thing I'm going to show for you is the simplest sort of truth table, and this is the truth table for the connective not, which we talked about last time. Now, how do you set up a truth table? A truth table kind of looks like in algebra you have, for example, x and y. X is your variable, and then you could think of x as your input and y as your output, if you like. And what you do is you make one column for x, one column for y, and then you put all the possible values for x in there. Not all the possible. You put some possible values for x, and then you put the result based on whatever function you have. We're going to do kind of the same thing with truth tables. Now, of course, with truth tables, with logic, there are only two possible inputs for your variable. What are those two possible inputs? True and false. Right? Because, again, to remind you, here we go. Okay. So we said, for example, in algebra, you have x, y. We typically use x, y, and z to represent our variables. In logic, we typically use p, q, and r to represent our statements. Now, in algebra, typically, what values does it take on? Any real number. Not always, but typically. In logic, what values do these take on? True and false. And then we also have to worry about all these different connectives, which is what we're going to get to right now. So, I've gone too far. Okay. So we're going to make a table. So in our quote-unquote x column, we're not going to put x. We put p, because p is what we typically use to represent the statements. Okay. Now in this case, we're making a truth table for not, so our expression is not p. Now we're going to write down every single possible value for p. What are all the possible values for p? Since we're in logic. True and false. Now when p is true, guess what value not p takes on? Not is going to make it false. Because what is not? It's the opposite. Now when p takes on the value of true, guess what not p is? I'm sorry, when p takes on the value of false, guess what value not p takes on? True. And that's a truth table. A simple one, but it's a truth table. Okay. So how would this look? So last time we also talked a little bit about making these actual sentences. So what would this look like if we're talking about actual sentences? Well, suppose the statement was P. Suppose the statement P was, it's cloudy outside. We drew the shades, but let's say that that's true. Well, what's the negation of that? Okay, so first of all, what is the negation in terms of notation? If P is the statement, what's the negation of that? Not P. In words, what would it say? It's not cloudy outside. And what would the value be? True or false? That would be false. Okay, so notation, words, value. Here's another example. Suppose P represented the statement, it's raining outside. And as we can tell at this moment, that's false. What would the negation of that be? Right. In terms of notation, what would the negation be? That's the words. In terms of words, it would be, it's not raining outside. What about the notation? Not P. And what would the value be? It's not raining outside. Is that true or false? It's true. You dig? Okay. Okay. So, in a nutshell, that's not. Not is fairly straightforward as far as constructing these truth tables. Next, the connective or. Okay. So remember, with or, you are connecting two different statements. So in this case, what are the two different statements that you're connecting? What's the first statement? It's cloudy. What's the second statement?
It's raining.
It's rainy. So if you say P or Q, that's going to say it's cloudy or it's rainy. Now, of course, in English we simply say it's cloudy or rainy, but let me make it a little more precise. Let me make it connect more directly to the math. It's cloudy or it's rainy. Okay. Now, is this true? Well, let's see. Is it cloudy? Well, we're saying it is. Close the blinds. Okay. So, yes, it's cloudy. Is it rainy? No. So, is this statement true? If I say it's cloudy or it's raining. It's true. Because what is, in effect, how can we interpret this statement of me saying it's cloudy or it's raining? All I need is one or the other. I don't need both. So this is true. So in the notation of logic, what we've got is true or false. And the entire statement is true. Because we only need, when we're talking about one or the other, we only need one. You dig? Okay. So here's another or statement. It's cloudy or my name is Jason. Now, it's cloudy. What's the value of that? True. My name is Jason. What's the value of that? True. So, this entire statement, is it true or false? This is true. Okay.
So the only way you get a false statement is both of them false.
This one says, this is a history class, or it is Wednesday. This is a history class. Is that true or false? It is Wednesday. Is that true or false? False. So what is the value of this entire statement? False. So Terrell, that answers your question. So exactly what Terrell said. When you have an or statement, P or Q, the only way for it to be false is both things have to be false. And now we're going to represent that on the truth table. Now, how do we write this out on a truth table? Well, we're gonna need a column for P, but what else are we going to need a column for? We're also going to need a column for Q, and then our last column is going to represent what? P or Q, our statement P or Q. So we go ahead and set that up. Now here's the trick. Before we only had P, and P is either true or false. Now we've got to worry about P, and we've also got to worry about Q. So P can have two different values, true or false. Q can have two different values, true or false. What we've got to worry about is all the different combinations. How many different combinations can we have? Well, what's one possible combination for P and Q? Okay. True and false. So true and false is one possible combination. What's another possible combination? False true. That's another combination. What else? True true and false false. Are there any other possible combinations? No. Pairwise, that's everything. Okay. Now when we have true true, what's the value of P or Q? True. When you have true false, what's the value of true or false? True. And false true, if you have false or true, what's the value of that? And then if you have false or false, what's the value of that? That's false. So there you go. So notice in particular that we needed one column for P, one column for Q, and then we need to write down every possible combination for trues and falses. And then our last column is the statement, which is our target, which in this case is P or Q. Next. So what's the other, or what's another connective that we learned last time? And. So let's do and. Okay. So let's take a look at the first one. So what if we have the wall is white and I teach math? Okay. So the first statement is, the second statement is, so the whole statement is true. So that's clear. Okay, so what if I said it's raining and it's Friday? The first statement, it's raining, is today. Right now it's false, and it's Friday. Statement is false. So altogether, this is false. Now, what about the statement it's raining and I teach math? Alright. Well, it's raining and I teach math. So first of all, it's raining. We said that's false. I teach math. That's true. So if I say it's raining and I teach math. Exactly. Because for an and statement, in order for it to be true, what do you need? Clearly you need both to be true. And in this way, our the way we use it in regular English also matches up with how we use it in logic. Okay. So now we can go ahead and make the truth table. And again, we've got P and Q, so we're going to have 4 rows with all these different combinations. And our last column is going to be P and Q. And again, remember, that's the notation for it. So for true and true, that's true. True and false gives you a value of false. False and true gives you a value of false. And false gives you a value of false for the complete statement. So the three that we've done, the three truth tables that we've completed so far and discussed for not, for or, and for and, did these make some sense? Y'all? Okay. All right. So now I want to talk about evaluation. In the case of evaluation, we only need to worry about figuring out the value for one particular case. So here we go. What is the value of not P and Q when P is true and Q is true? Look at the question. The statement is not P and Q.
Oh,
Okay, and how do you know that?
because if P and Q is true, then not P will be false.
Exactly. Okay. Now, how can we figure this out? Well, remember before I made the analogy with algebra. So you know what? Guess what you can do to figure this out? Plug it in. Right? Because remember, P and Q are in a sense variables. But what are we being told here? The value of the variables. So we have not, and what's the value for P? True. And then Q, and what's the value for Q? True. So this is the statement that we've got. Now we can go ahead and quote unquote calculate, but in logic we call it evaluate. So what's the next thing that I need to evaluate?
What is not P?
Right. So but now it's not true.
Or not true.
So not true is the same as false. So now we've got false and true, and what's the value of that? And the value for that is false. Okay, so does that make sense? Alright, so all you gotta do is plug it in. Alright. So here's a fun one. Evaluate this P or Q and not Q when Q is false and P is true. So notice that as I make these statements a little bigger, you can't just sort of eyeball it. You actually should write stuff down. So what do we plug in? Not, and what's Q? Not false. Okay. So what's the first thing we can evaluate? Okay, so what's the value of the or statement? It's true. And then we have an and now what?
And not false, which is true.
Not false and true. And what's the value of this? True and true. True. Okay. I'm glad it's easy. You can do this one. Give it a try. Okay, so somebody wants to tell me how to do this. Let's see. You had an answer. Okay, so tell me how to do it. Just tell me what you wrote down. Okay. Uh-huh. Good. Is that straight? Yeah, so you do know how to explain it. Okay, good. Okay, so now we're going to take this. We're going to take these trickier statements, and we're going to take the truth tables that we made. Now we're going to do truth tables for trickier statements. So notice that when we do evaluation, you only figure out the value of a statement for one possible configuration of trues and falses. Now we're going to figure it out for every configuration of trues and falses. So, how do we do that? Let's see. Oh, we talked about this. That's okay. All right. So let's, okay. Sorry, I'm going to come back to all those words. So let's make a truth table for P or Q and not P. Okay. So how do we make a truth table for this? So first of all, what is our first column going to be? P. What is our next column going to be? Q. Now here's the rub. What's the next column? Yeah. Our next column, look, our next column could be P or Q and not P, but we'd have a devil of a time figuring what the value was. You can't just straightforward, it's not as straightforward as simply P or Q, where you can see it directly. So when you make a truth table for a tricky statement like this, you're going to have to build up the pieces. So once we know the value of P and we know the value of Q, what other values are we going to need to know in order to figure out the value of this? We're going to need not P, as Kane said. And what else are we going to need?
Not Q.
Do we need not Q? Not for this one. We need Q and not P. Exactly. Now once we know the value of P, Q, not P, Q and not P, do we then know all the pieces and can we say the value of this statement? Yes. So our truth table is going to look like this. At least the heading. So notice that you need to, I've highlighted it so you can see how all the different pieces break down. Right. So it's still true that your first column is Q, it's still true that your second column is P, and it's still true that your last column is your entire statement, which in this case is P or Q and not P. The thing is that in order to get from P, Q to your whole statement, there are some middle steps. You need to figure out the value of those things. So in this case, what are those middle steps? What are the things that we also need to know the value of? As we just said, you also need to know not P, And if you look at the entire statement, you also need to know the value of Q and not P. So we're going to need a column for that. So I will spot you the first row so we can talk about it. So in our first row, what's the value of P? Value of Q? I like to start true and true. That's just me. Okay. So if we have true and true, then what's going to be the value of not P?
False.
P is true, not P is false. Now what's the value of Q and not P?
False.
Right, because Q is true, not P is false. You take an and on that, you get false.
So why is P not true or not false?
Sorry?
Why is P not false and why is true not false?
Well, we're doing all combinations. So the first combination I'm doing is true, true. So finally, we're going to evaluate P or Q and not P. Now, what's the value of P?
True.
True. What's the value of Q and not P?
False.
False. So you have true or false, which gives
True.
true. So notice that making a truth table for these tricky compound statements is probably going to take a while. Because you have to do, it's not just evaluating where you just plug it in and see what you get. It is literally writing out every single part for every single piece and then doing it for every single combination. So, next. So what's our next combination for P and Q that we're going to check out?
True and false.
True and false, and then false and true, and then false and false. Okay. So, when you have true and false, what's the value of not P going to be?
False.
It's going to be false. P is true, so not P is false. And then so let's just go ahead and fill everything in. So this was true and true, that was false, false, true. Okay. So next is true and false. Not P is going to be false. Q and not P is a false and a false, so that's false. And then we've got true or false, that's true. Next. What's the next combination we're going to cover? False and true. I like. Okay. And then we're going to also do false and false as the last one. Okay. So for false and true, what's the value of not P?
True.
That's going to be true. Now Q and not P is true, because that's true and true, so it's true. So finally, P or Q and not P.
True.
It's true and true, so it's true. Finally, what's the value for false and false? What's the value of not P?
True.
True. What's the value of Q and not P?
False.
That one's false. And then finally, what's the value of P
True.
or Q and not P?
It's true.
Well, this is a false or what?
A false and a false.
It's false or false. So it's false. And there you go. So we have every combination. We've worked out the value of the statement for each one. That's the whole truth table. Alright. So, in my estimation, the hardest thing about making these big truth tables is you have to figure out all the columns that you need. Yeah. So let's continue to work on that. So let's draw the truth table for not P or Q. So, what's the first column that you're going to need? P. What's the next column that you're going to need? 2. And what's the next column you're going to need? You're going to need a not P. Do we need not Q? No. Oh, what's the next column that we need? We've got to put something in before we do that. What is sort of like the next biggest compound statement, but it's not the whole statement? Not P or Q. Exactly. Not P or Q. And once we have that, what are we ready to do? Then we're ready to do the whole thing. Not P or Q. Okay. So again, just think about building this up from the smallest pieces. And again, also, it helps to think of this in terms of algebra. In terms of algebra order of operations, or algebra-like thinking, I should say. Of course, it's logic. What's the first thing that you would evaluate if you went into this statement? The inside, exactly. And then what's the inside? Right. So what's the first thing that you would need to evaluate in there? Not. So inside the brackets, you're going to need a not P or Q. We've got a column for that. In order to evaluate not P or Q, what do you need to know the value of? You need not P. So that has to get its own column. Then you need a Q. That gets its own column, but we already have that. Does that make sense? Okay. Sorry? Okay. You need to go in and figure out, and it helps in terms of order operation. It helps by using order of operations, logic order of operations, as to what you're going to need the value of in order to figure out this whole thing. So, in terms of the whole statement, that's going to be the last column. Then, if you like, what's the innermost piece of this statement? Well, there's a not P in there, so that needs a column. Then you've got or Q, so Q needs a column, but Q already has a column. Then you're going to need not P or Q. That gets its own column. Then you need not of not P or Q. But that's the whole statement, so that's your last column. So again, think of it in terms of order operations. You're building it up piece by piece. So now we're ready to make our truth table. So we've got true, true, and what's the next combination? Oh, no. First I'm going to write down all the combinations. Sorry. Okay. So true, false, and then false, true. That's the tail of the Q. It's true, true. Okay. So now let's evaluate one by one. So for true, true, what's the value of not P? False. Now what's the value of not P or Q? That's true. And so finally, what's the value of the whole thing? False, because it's just not of that. Okay. Next, what's the value of not P? False. What's the value of not P or Q? That's false or false, so it's false. And then? True. Okay. Next, what's the value of not P? True. And not P or Q? It's going to be true. And then not of that? It's going to be false. And then last line, what's the value of not P? It's true. What's the value of not P or Q? It's false or true, so it's true. Or true or false, rather. And then not of that? This is false. So there's your whole truth table. Okay. So does that make a bit of sense? Okay. So hopefully I'm going to now let you work on one by yourselves. I'll give you a minute to work on that. Hopefully you're ready for it. So give it a go. Okay, so someone lead me through this, and then if someone has a question as we're doing it, just shout it out. Okay, so who's going to help me out?
You have a four statement. You or not P.
I'm sorry. So what's the first column?
P.
Mm.
Not Q. Q or not Q. And then P or Q or not
Okay, so okay. And first row. Okay. And then next row. Okay. False, true, 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 true. Okay. Okay. Okay, so thank you, Terrell. Does everyone agree with this, or do you have any questions about it? Is that good? Okay. So it seems like there are no questions, so that's good. Now, yes, question.
For the second row, for Q or not P, not false.
Okay. So this one right here?
Yeah.
Okay. Yeah. Because Q is false, not P is false, you get false or false. So that's false. What about the final one now? That's still true. Because you get true or false, so that's true. Okay. Okay, good. Now, what unusual thing do you notice about this truth table? Yeah, it's always true. Doesn't matter if P is true or false or Q is true or false. This statement is always true. Well, I did a little magic in there, but whatever I did, it's always true. This is a very special situation and it's a very special name. This is called a tautology. And I'll give you the most simple and most foundational tautology in logic. P or not P. Now, we could make a truth table, but I want you to understand, let's talk it out and see why this is always true. Well, what happens if P is true? And you get true. And what happens if not P? What happens if P is false? And then you get right. Or just in terms of words, when is an or statement true? All you need is one to be true. So if you got P or not P, well, one of them's got to be false and one of them's got to be true. So the or statement will always be true. One of them has to be true. Okay. Okay, good. Next. Oh, and by the way, a little extra credit thought question. What does this logic actually, we're not going to talk about this too much, but logic actually has connections to set theory. So does this remind you, what could this remind you of in terms of set theory? Yeah. You've got P, and then you've got P complement. And OR is like which set operation? It's like the union. Alright. And again, this is an extra credit thought statement, so I'm going to leave it alone and let you think about why those things make sense, if you like. Okay. So for example, a possible extra credity sort of question on an exam might be translate a set theory statement into a logic statement or vice versa, and then explain why that makes sense. For example. Okay. Back to logic next. Okay. So we got two truth tables to set up here. So first, we're going to make the truth table for not P and not Q. So in order to do this, what columns do we need? We need P and Q, of course, and then not P, not Q. What else? Not P and not Q. Okay. So we're going to have true, 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 false, false, true, false, false. Okay. So in the first row, what's the value of not P? False. Not Q? False. Not P and not Q. That's false and false. That's false. Next. The value of not P is false. The value of not Q is true. So not P and not Q is false. Next. Not P is going to be true. Not Q will be false. Not P and not Q, true and false. That's false. Next, not P is true. Not Q is true. Not P and not Q is true and true. That's true. So that's the truth table for not P and not Q. Next, let's draw the truth table for not P or Q. So what columns will we need? We're going to need P, we're going to need Q, what else? P or Q, and then what else? Well, and then we need our last one. Not P or Q. Okay, let's check it out. True, 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 false, false, true, false, false. Okay, now, P or Q, in the first row, P or Q will be true or true, that's true, and then not of that, false. True or false, true, and then it's not of that, so it's false. Next, P or Q is going to be true, so you get false. And then false or false? False. So finally that gives you true. Now I did these two truth tables side by side for a reason. What do you notice about these two truth tables? They have the same result. So these two statements always have the same value. Doesn't matter what P is and what Q is. So when two compound statements have the same truth table, they're called equivalent. Which makes sense. That means whenever you see not P and not Q, it would be equivalent simply to write down not P or Q, or vice versa. One can replace the other. They'll always have the same value. So first of all, these two statements are equivalent. That's the first thing. The second thing is, this is a very important equivalence in particular. I probably should have flipped them. Let's look at the one on the right. What is the one on the right? Well, in particular, notice we've taken P or Q, which is a very basic sort of statement that we deal with, and then we've taken the negation of that.
Not trying to confuse anyone, but if you were to take the not on the right side and put the flag to the P on the P, it would be the same thing anyway. It's kind of like if you were multiplying and you were negative on flag to put in the P, and then the numbers would be negative P and negative P. So
Okay, sort of. Okay, so right, but this is exactly it. We'd like to say if you have basically you're on the right track in that we've got a statement in parentheses and we've got a negation of that. So in a sense, Jonathan is asking or saying we want to talk about how do we quote unquote distribute that not. Well, what happens? Well, we just showed exactly what happens. If you take the not of P or Q, what do you get? No, what do you get?
Not P or not Q.
No, what do you get?
P and not Q.
You get not P and
Oh.
not Q. You dig? But that's what we just showed. Is that not P or Q is the same as what? Not P and not Q. So this is part of what's called De Morgan's law for making these negations. So now there's a reason why. Here, there's the equivalence. All right. Now there's a reason why it looks like this, and there's a reason why this actually makes sense. Let's think about it. So we proved that it's true. Great. Proof. What does a proof mean? Well, let's actually think about why this makes sense. Why not of P or Q gives you not P and not Q. Suppose that you have an or statement. What does it take for an or statement to be true? All you need is one of them to be true. On the other hand, what does it take for an or statement to be false? And that's exactly what this is saying. In order for the or statement to be not, in order for it to be false, what has to be true? They both have to be false. Does that make sense? That's what the and statement is saying. It's saying you have not P, in other words, P is false, and you also have not Q, or in other words, Q is false. And that's the same, and that's what would give you, or that's the same as saying not of P and Q, or in other words, not of P or Q. P or Q is false. P or Q being false is the same as P being false and Q being false. And when you say not P, what you're actually saying is, if you just made the statement not P, what you're actually saying is not P is true, which is the same as saying that P is false. If you want them to have the same value. If you want these two compound statements to have the same value. So there's another half of De Morgan's law. So here we learned how to negate an or statement. Guess we're going to see what to negate next. An and statement, absolutely. I'll tell you what, I will let you guess what that law is going to be. The negation of P and Q is going to be what?
You have like with R, like this, but you have like the same.
Right, so say it out.
So it would be the negation of not P and Q.
Right, so the negation of P and Q is going to be the same as,
Not P or not Q.
there you go, not P or not Q. And it's for, I mean, again, you're switching the ands and ors around, but it's the same idea. When is an and statement true? Not when they're the same. When they're both true. Exactly. But here we're saying not of that. So when will an and statement be false? All you need is one of them to be false. But that's exactly what it's saying on the right side. All it's saying is that this will be true when either not P, in other words P is false, or when not Q, in other words when Q is false. So on the right it's simply asking for one of them to be false, which is what we just said is exactly what we need. The same thing on the left. So if you talk it out, you realize that both statements are asking for the same thing. So if all of that makes sense, that's great. If you like the proof, that's great. But finally, to help you out, I have a little verbal shorthand of how to remember each of De Morgan's laws. Or as Jonathan said, how do you distribute the not? How do you distribute a not? Negate both and switch the operation. So, and again, that's just memorizing the actual technique. Although we've seen, if you talk it out, we've actually seen why that makes sense. Okay, now, so last thing, we've got the statement, or the compound statement P and not Q or R. We're going to draw the truth table for this. So, what columns do we need? We need a P, we need a Q, and we need an R. Do we need a not P? We need a not Q. Then we need a not Q or R. And then finally we'd be ready for the whole thing. Okay. Listen. Alright. Now, here in particular, I want to emphasize the fact that we're going to write out. So we've got P, Q, and R. I want to emphasize the fact that we're going to write out first all the possible combinations of P, Q, and R. So let's set about trying to do that. So what's the first combination? Okay. So in order to do it in some organized sort of fashion, let's start with true, true, true. Then what's another possibility? Okay. So true, true, false. is a good next one. Okay, now what?
True, false,
True, false, false, and then what else?
true, false.
And then, sorry? Okay. True, false, true. Now what's another possibility? Yeah. False, true, true, and then false, I'm sorry?
False, false, true.
Okay. So I think you guys kind of have the idea. You said false, false, true, and then what's another one? False, false, false. Okay, I'm going to push that back. And then what else? False, true, false. Okay. So you got all of them. But I'm going to say that you did it in a slightly haphazard sort of order. So I'm going to rearrange these so that it's more organized, and you can always make sure that you get every possible order. Okay. So first I want to switch those, and then I'm going to run these around as well. Okay. Yes. I don't think that would make sense. You write down every combination and then evaluate it. No, because remember you have to write down every combination of P, Q, and R together because they're all being evaluated in the same statement. I think that answers your question. No? Okay.
See how you have all the truths there, right?
Yeah.
All the combinations of the truth. I'm saying can you do another table with all the combinations of false, so you won't get a mixed up.
I don't recommend it. Okay. So notice that what we're doing here is, what's one possible combination for P and Q? It's true, true. Well, given that, what are the possible values for R? Either true or false. Next, another possible combination for P and Q is true and false. Given that, what are the possible values for R? True and false. Next, what's another possible combination for P and Q? False and true. Now, given that, what are the possible values for R? True, again, true and false. So you could have false, true, true, and false, true, false. And what's another combination for P and Q? False, false. And when you have false, false, what are the possible values for R? True and false. Which will give you false, false, true, and false, false, false. So notice that in this case, we've already said, first we're going to do true, and then we're going to do false. So R goes true, false, true, false, true, false, true, false. Q winds up going true, true, false, false, etc. P goes true, 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 false, false, false. What you wind up is having for each possible combination of PQ, true and false for R. Right. Because for each combination for P and Q, R goes true then false. Then you get to a new combination for P and Q, R goes true, false. And that's also the reason why Q comes in blocks of 2. Because it keeps the same value when R goes true, false, but then it's on to the next combination. Yeah, Marcelo.
So are you reverse?
Yes. That's one way to look at it. Okay. So we could take a minute to fill out the rest of the truth table. But I want to make this point. I think we know how to do the rest of it, but I want to make this point. That's a lot more rows than we had before. In fact, how many rows do we have?
5.
We had 4 and now we have 8. How can you predict how many rows there will be in your truth table.
The number of
You want to just take each and then multiply.
Right. So how do you know ahead of time? We already made the truth table. We know how many rows there are going to be. How can you predict ahead of time how many rows there will be? Yeah, Lance. It's 2 to the x. Exactly. And what's x? However many variables you have. Exactly. And why is it 2 to the x? Just because each one is true or false. Exactly. So this isn't a course on combinations and permutations or counting, but if you know a little bit about that, you'll know that 2 possibilities for P, 2 possibilities for Q, 2 possibilities for R. So how many total possibilities? 2 times 2 times 2. 2 to the third. Okay. Any questions? Okay. Great.